Okay, now that we've played around with fmap2, fmap3, fmap4, and we've seen what some kinds of things that the applicative type class lets us do, I want to actually show you the definition of the applicative type class itself. So we'll call it, I'll call it applicative prime for now, so I don't actually conflict with the one coming from the standard library. So of course we have this arbitrary. You know what? Okay, I'm not even going to worry about conflicting. I'm just going to show you the definition in a comment. So of course we have this operator, which we saw before. Okay, but there's actually one other operator in the applicative class as well, and it's called pure, and it simply has the type A to FA. So to explain where this is coming from, let's actually think about, so the type of fmap looks like this, right? And we defined this fmap2 using applicative that looks like this. Let's see, I'm going to line this up here. And we saw that we can define fmap3 and so on. Okay, what would come right before fmap? So I argue the proper way to extend this pattern downwards would be, instead of having a function here, right, here's a function of a single argument, here's a function of two arguments. I don't have a function at all, I just have a value of type A, and then I just return an FA. And that's exactly what pure is. So it fits right into this hierarchy. We could think of pure as like fmap 0. And all it does is it lets us take a single value of type A and sort of inject it into the F world in some way that makes sense. And that's going to be different for every F, but we require that every instance of applicative has this pure thing as well. So one thing we could do with pure, for example, you know, we'll call this lift x. I don't know, I don't really know what this is for. Just an example. But if we had, this is going to look kind of like fmap3, except we're going to have, instead of having an FB here, I'm just going to have a B. Right, so I want to take this function a to b to c to d and apply it to some arguments, and some of them live in the F world and some of them don't. Right, so this B one doesn't. Can I implement this? And yes, I can. All I have to do is take this B and lift the B into the F world using pure. If I apply pure to it, I'll get an FB, and then I can use the normal applicative stuff to apply this function. So G F A B F C. This is going to be equal to G fmap FA app, and I can't just say B here, I have to say pure B FC. Okay. We'll talk a little bit more later about why it's called pure. Really quickly, the intuition is that this F thing might somehow encapsulate an idea of effects. So you know, this represents some kind of computation that will give you an A, but they might have some effects along the way. And so pure creates a computation that doesn't have any effects. It's pure. Don't worry about that too much. That's just some intuition, but we'll talk a lot more about that as we go on. The next thing that I want to show you is that given pure and app, I claim that if we have these two things, then we can actually implement fmap. And that would mean that every applicative is automatically a functor, right? Because given these things, you can use them to implement fmap, and that means we could make a functor instance. So let's see how to do that. So I'll call this fmap prime. So my claim is if we have an applicative instance for f, then we can implement. So here's the type of fmap, and the question is, can we implement this using only pure and app? And I'll let you think about this for a minute. You should pause the video and see if you can do this yourself. Okay, so let's, we're given this G, that's a function from A to B, and we're given an FA. So what should we do? Well, app, right, we can apply a function-like thing to an argument-like thing, but the function has to be inside of an f. And I just have a plain old function. Okay, so I can use pure to lift this function into the f world, right? Then I'll have an f a to b, and then I can use app to apply that to this fa. So all I have to do is to say pure g app fa. And that certainly has the same type as fmap. Now, you might wonder, there might be some f's for which fmap does one thing, and this, whatever this is, although it has the same type, does something else. That's certainly possible, but remember how the functor class had some laws that we required it to satisfy? And we're also going to require that applicative has some laws, and the most important one to know about is that we require that this is actually the same as fmap. Okay, so applicative law, it should be the case that fmap g fa is equal to pure g app fa. Okay, so whatever fmap, pure, and app do, they should be related in this way. And that's actually going to help us a lot as when we try to come up with some example applicative instances. We can use what we already know about how fmap works to guide our ideas about how we might implement pure and app.